Welcome back to the lecture series in wave optics. In last few lectures we have discussed the interference phenomena, how this interference phenomena can observed in different cases such as thin films, Newton's ring, etc. Now in this lecture we will start to discuss a new light phenomena, that is called diffraction. Please look at this beautiful picture. This is an image of a razor blade. We expect the edge of this shadow is sharp one, but in actual this image is not at all sharp when viewed under the magnification. There are few alternate dark and bright region you could observe in this region at the edge of these shadows. This is a quite interesting phenomenon. Why this type of light pattern formed? And what are the phenomena? What is the phenomena behind this? When we see this in detail, we can understand this is because of the diffraction phenomena. So in this lecture, in this session, we will discuss what is basically diffraction. When a wave incident on an obstacle or a small openings, then the light bend around the edge. Suppose this is the obstacle, then when the light travel, then light bent at the edge of that obstacle. This bending of light wave around the edge of an obstacle is called diffraction. You may just remember that this phenomena is significant when the dimension of the obstacles are comparable to the wavelength of light. That is, when the opening is very large compared to the wavelength of light, the wave does not bend around the edge significantly. When the opening is very small, the bending around the edge is noticeable. Then you can observe a diffraction pattern or a alternate dark and bright regions in the shadow region. The edge of razor blade, you know that that is very sharp. Therefore, we could see a diffraction pattern in the image of a razor blade. So this is about the basic things about the diffraction. Now before we discussed about the diffraction, we need to have some basic understanding of few things. So one among is the Huygens theory. We have already been studied in our early classes, or we are very familiar that the light propagate in the form of wave front. So let us assume this is a wave front. This is a wave front. Now Huygens theory, we are very familiar with that theory, that every point in the wavefront act as a source of spherical wavelet. So you can take any point of this wavefront, then that is creating certain disturbance. That disturbance is acting as a source of a spherical wavelets. So this is of spherical wavelets. This is another. This create another wavelet. This create another wavelets. And the envelope of these wavelets will be creating the position of the next wavefront. This is how the wavefront spread out in forward direction, and this spread out of the wavefront is in the speed of light. The sum of these spherical wavelets and their envelope form the new wavefront as we have discussed. So according to the Huygens theory, each point in a progressive wave produces a secondary wave, and the envelope of that secondary wavelet is giving rise to the position of the secondary wave front. So this is the concept of the Huygens theory. This is how the light propagate in the form of wavefront. That is what exactly the Huygens explained. See this picture. Here S is the source of light which sends certain cylindrical or spherical type of wavefront towards a small opening Mn. So, here Mn is a small aperture where the diffraction take place. Now, we place a screen xy in front of that path of the light. Now, we are expecting AB, this is a region, this region is supposed to have illuminated portion on the screen, and above and below this A and B. So, this region and this region we are expecting the geometrical shadow. Now, considering Mn is a primary wavefront. So, here from M to N, this is only the part of wavefront which is passing through the aperture. So, we are considering Mn is the primary wavefront. Now, according to the Huygens construction, the secondary wavefront are drawn from Mn. That means, every point of this M and Mn wavefront is acting as the source of secondary wavefront, that is sending the secondary wavefront, and you can draw the wavefront from here like this. That we can expect the encroachment of the light towards the geometrical shadow when it is moving. Obviously, this wavefront will be reaching in this region as well as in this region as well as above the point A and below the point B. So, there will be an encroachment of light towards the geometrical shadow. Obviously, the shadow does not form a sharp because the light is spread out towards the geometrical shadow region, that is the diffraction. Similarly, we can find the diffraction effect in case when we place a small opaque, Mn is an opaque region in front of the source S. Here we expect the geometrical shadow again in this particular region in between A and B. Here we are expecting a sharp edge of this shadow above the A and below B. So, however, the light wave front spread out, you know that. So, this part of the wavefront and this part of the wavefront is acting as the primary source of wavefront, that will be spreading the wave secondary wavefront, and obviously we expect this wavefront will be spreading out of this region and this region. Obviously, in this case also the edge of the shadow is not sharp. So, this is what is exactly the diffraction. Now, there are a few assumptions has made by A.J. Fresnel, the scientist who has combined the concept of Huygens theory and tried to explain the bending of light around the obstacle with a few assumptions. Now, according to the Fresnel, the resultant effect at an external point due to the wavefront will be depends on few factors. For example, look at this picture, this is a source of light. Now, this source of light is sending the cylindrical spherical wavefront towards the slit Mn or the aperture Mn. Now, Mn is the wavefront which is passing through this aperture. Now, there will be some effect at the P. So, because of that effect we get a diffraction. What we see here MCN is the wavefront due to the point source S, and we obtain the resultant effect supposed to be at a point P. Now, what Fresnel assumes that a wavefront can be divided into into large number of small regions or small strips, like this I am considering small regions. Each wavefront is considered as a very small regions or strips, and you can see this is as a zone, and these zones are called Fresnel zones, and it is of very small area, and the resultant effect at any point will depends on the combined effect of the secondary wave emanating from the various zones. So, each zone is sending certain secondary wave towards a point P. So, this zone, each zone will be sending certain wave front or certain wave front from the each zone. So, the resultant effect will be the combined effect of all this. And the second assumption is the effect at any point due to any particular zone will depends on the distance of the point from the zone. For example, if I consider the point O. So, point O is least distance from the point C. So, the point C will be creating the highest effect at point O. However, this particular zone, the distance is larger than CO, therefore, its effect will be less. So, that is the concept. So, the effect at any point depends on the distance from the zone. And the third assumption is the effect at point P or any point will be depends on the obliquity of the point with reference to the zone under the consideration. What it does mean? If I consider the obliquity here, this is the obliquity from here theta. Now, as if I consider this particular point, this is the obliquity, and if I consider another point over here, then the obliquity increases. As the obliquity increases, the effect will be decreases. So, what is the concept here? What is the third assumption? The effect of point P depends on the obliquity of the point with respect to the zone under consideration. Now, you can say the effect at any point due to the obliquity factor is proportional to 1 plus cos theta, where theta is the angle PCO. So, here this is an angle we are considering, this is the angle theta. Now, let us consider an elementary wavefront at point C. So, this is the point C, we are considering the wavefront. Now, when theta is equal to 0, so this is the wavefront we are spreading, we are considering. So, theta is equal to 0. When theta is equal to 0, cos theta is equal to 1. So, that is a maximum value. So, 1 plus cos theta will be maximum when theta is equal to 0, then the effect will be maximum. Similarly, in the direction tangential to the primary wavefront, that means this is the direction. So, in that direction the theta is 90 degree, then obviously cos theta is equal to 0, then 1 plus cos theta becomes 1. So, this is only term, this will be 0. So, that means the effect will be reduced by half. And another possibility is in the direction CS, in the opposite direction. Then here in this case theta is equal to 180. Now, that 180 will be giving you the value cos theta is equal to minus 1. Now, then 1 plus cos theta becomes 0, this complete term becomes 0, then that is the effect is 0. This reduces, you remember this reduces one of the difficulty experienced in the with the simpler form of Huygens principle itself, that if the secondary wave spread out in the all direction from each point on the primary wavefront, they should also give a wave travelling forward as well as in backward direction as well, but also. So, with this concept there is no back wave at all. So, that solve a problem occurred in Huygens principle. Now, we will discuss another concept of the light using this Fresnel-Huygens assumptions, that is the rectilinear propagation of light. How the light propagate in straight line with the concept of wavefront. Now, in this picture let us consider a plane wave. A, B, C, D. So, this is a plane wavefront or a and we are considering the shape as a rectangular plane wavefront. Now, P is a point at a distance B. So, P is a point. At this particular point, we need to calculate the what is the effect. We need to estimate what is how the effect is. So, what we need to find the resultant intensity at point P due to the plane wavefront A, B, C, D. So, first of all, what we need to do? We have to divide the wavefront into small half period elements or zones. These zones are called Fresnel zones, as we discussed in the Fresnel assumptions. So, first of all, we have divided this wavefront into small zones, like these are small zones, many zones we can consider here. Now, we have to find the effect at all the zones, we have to find the effect due to all zones at point P. Now, you remember each zones create a path difference of lambda by 2. What I mean to say, the light from one zone, and if I take the light from the another zone, there will be a path difference of lambda by 2. Therefore, this is called it as half period zones. Now, if this distance is B, from O to P it is B, then the distance from M1 to P should be B plus lambda by 2. That means, the this ray is from the first zone and this ray is this light this wave from the second zone. Therefore, there should be a path difference of lambda by 2. Similarly, from M2 to P there will be another addition of lambda by 2, that will be 2 lambda by 2. So, this distance will be B plus 2 lambda by 2, and when the light coming from M3, the third region, then that will be giving you a 3 lambda by 2 path difference, addition of 3 lambda by 2 path difference to the B. That means, the distance will be B plus 3 lambda by 2 and so on. So, what we have discussed, these circular zones are called half period zones or half period elements, because each zone differs from its neighbors by a path difference of lambda by 2. That is, the secondary waves starting from point O and M1 and reaching at point P will have a phase difference of pi, because there is a path difference lambda by 2. If there is a path difference corresponding to that path difference, there will be a phase difference of pi. Now, we are just taking the distance OP is B from the speaker. Now, OM is this difference, that difference is the radius of the first zone. Therefore, that is taken as R1. Then OM2 is the radius of the second zone, it is taken as R2, and OM3 is taken as R3, that is the radius of third zone. So, as we have discussed, M1P is equal to B plus lambda by 2, and M2P is equal to B plus 2 lambda by 2, M3P is equal to B plus 3 lambda by 2. Now, we have to calculate the area of the each zones, first half zone, then second half zone and third half zone. So, in order to have the simple understanding, I am considering a cross section of this 3-dimensional view. This is it look like a 3-dimensional view, and it is 2-dimensional picturization I am taking. So, that this is the point O and this is M1, this is one of the point in the first region and second region, third region, so on, right. So, OM1 is R1, this distance. So, let us find the area of the first half zone. So, you know that area is pi into OM1 square, that means pi r square is the area of a circle, that will be giving you pi into OM1 is b plus lambda by 2 all square minus b square. So, yeah, there is a. So, once you expand this as a plus b all square, then you can cancel out b square and b square term, then we will have the formula pi into b lambda into lambda square by 4. So, you can have this pi OM1 square is equal to pi b lambda, because this lambda square by 4 is a negligible term, because lambda is a wavelength of light that is in the order of angstrom, and obviously if I take the square and dividing by 4, that will be giving you a negligible value. So, we are just neglecting that one, and then pi OM square is equal to pi b lambda, where b is the distance, lambda is the wavelength of the light itself, and OM1 is nothing but the radius of the first zone, then pi r1 square is equal to pi b lambda, and if I cancel this pi and pi, then I will be getting r1 square is equal to b lambda, and therefore, the radius of the first zone r1 is equal to root pi b lambda. Similarly, you can calculate the radius of the second zone as well. So, in that case we will be taking pi o we will be taking pi OM2 square, the same way the same method we are using in this case also. So, we will be taking this is as the triangle. So, yeah, the area we can calculate by using this formula pi into b plus 2 pi by 2 all square minus, obviously there is a pi term over here, yeah, there will be pi term over here, pi b square, and again pi r2, or you can take this as a square root, then there is no need of this pi over here. So, pi r2 square can be written as pi into b plus lambda square minus b square, again you expand this as a plus b all square, and you can find b square and b square will be getting cancelled out, and again there will be a term as we have discussed, lambda square divided by 4, that can be neglected since lambda square is a very negligible term, and then you can easily estimate r2 is equal to root 2 b lambda. So, we have discussed we have derived the equation for radius of the first zone as root b lambda, and we have discussed the radius of the second zone as root 2 b lambda. Now, we have to calculate the area of the second half period zone. What is the area of the second half period zone? Second half period zone is this one, this zone is the second half period zone. So, we are finding the total area here, we are finding this is the circle of radius r, and there is an inner circle that is of radius r1. So, once you have this total area, you have to reduce, you have to subtract the total area, you have to subtract this inner area of the inner circle from the total area, then you can obviously obtain this particular area value. So, we are finding the area of the second half period zone as pi r2 square minus pi r1 square, that will be giving you pi into 2 b lambda minus pi b lambda. So, this area you will be getting as pi b lambda. So, this is the area of the second half period zone. We have already derived the formula for the first half period zone is pi b lambda, and again we have derived the area of second half period zone is pi b lambda, that is the area of each zone period is equal, that is equal to pi b lambda. Also the radius of the first half period zone is b lambda, root b lambda, it was second half, the radius of the second half period zone is root 2 b lambda, and third is going to be obviously root 3 b lambda. Therefore, the radius are proportional to the square root of the natural numbers. However, it should be remembered that the area of the zones are not constant, but are depends on the term lambda, the wavelength of light, and again b, the distance from the point from the wavefront. So, the area of the zone increases with increasing the wavelength of light. The secondary wave reaching at point P are continuously out of phase. So, from one region, one zone, the wave from one zone and the wave from another zone, they are out of phase. So, continuously out of phase and in phase with reference to the central and the first half period zone. Let us say M1, M2, M3, for example M1 is the supposed to be, M1 is the amplitude of the light wavefront from the first zone, and M2 which is in the out of phase. So, M2 the amplitude is in the downward direction, this was a upward direction, and again M3 is out of phase with M2, then that means M3 is in phase with M1. So, in this way we are having different amplitude, and again you remember the distance from the first zone, second zone, third zone, which obviously decreases. Therefore, the amplitude of M1, M2, M3 etc., that will be decreases. That means, this M1 is slightly greater than M2 and which is again slightly greater than M3 and so on. So, M1 and M2 which are in out of phase we have discussed, and M3 is in phase with M1. It is because the phase difference, there is a phase difference of pi between these two wavefront coming from the two consecutive zones. So, if we have the odd number of zones, that will be giving the last wavefront will be giving in the up direction, and due to the even number, if there is even number of zones, then obviously that will be giving you the displacement at the last amplitude which is in the downward direction at the same instant. As the amplitudes are gradually decreasing, so you can find this M2, the M2 is approximately which is the average of M1 and M3. So, you can say M2 is equal to M1 plus M3 divided by 2. So, the resultant amplitude at point P will be giving you first M1, that is I am taking it as positive, then we have M2 that is in the downward direction, therefore, I am taking M2 minus, then M3 is in phase, then M4 is in out of phase and etc. So, this is how. And again what I am doing here, I am this is the resultant amplitude, this is the resultant amplitude A. So, I can write A is equal to, now M1 I am splitting into 2, that means M1 by 2 plus M1 by 2 simply, then I have minus M2, then I have M3 I am just writing it as by splitting it, M3 by 2 plus M3 by 2, M3 by 2 plus M3 by 2 will be giving you M3 itself, then again we have minus M4 and plus M5 by 2 plus M5 by 2. There is nothing, no changes at all, but I am for the convenient or for reducing this formula, then I am just writing like this. Then now you know that M1 plus M3 by 2, that will be giving you M2 itself. So, this entire term will be getting cancelled out. So, what left over here, M1 by 3 So m1 by 2 will be left over here. Again here m3 by 2 and m5 by 2, that is the average of m1 and m3, that is the value of m4, therefore this term also getting cancelled out. So what left over here, the amplitude A is equal to m1 by 2, this is left in the first case, m1 by 2 plus, and the last term will be existing if it is an odd number, that means mn by 2. So, if the zones are odd number of zones are there, and even if there is even number of zones, then we will have the amplitude A is equal to, obviously m1 by 2 will be there, then we have to consider two terms. First m n minus 1 by 2 and there will be last m n by 2 if there are odd number of even number of zones, if n is even. Well, as n tends to infinity, now you remember m n is the amplitude from the last zone and n tends to infinity. So, the value of m is approximately is 0, that therefore, so we can consider m tends to be 0, since the amplitude gradually diminishing order in the diminishing order, then the resultant amplitude you can take it as A is equal to m1 by 2 itself, because these term, whether it is coming these two terms, the amplitude of these two terms are negligibly small. So, I am just taking it as amplitude is equal to m1 by 2. If this is the amplitude, then obviously the intensity is proportional to square of this amplitude, therefore, I can write the intensity I is equal to m1 square divided by 4. This is quite interesting. The intensity at point P is only 1/4 of that due to the first half zone alone. Here only half of the area of the first half zone period is effective in producing the illumination at the point P. So, with this I am ending today's session here. We will meet again in another session with another topic. Thank you.